Long before the first dinosaur had ever drawn breath, Earth was already filled with life. Across the immense continent of Pangaea, saber-toothed predators patrolled sprawling floodplains. Strange herbivores moved through forests of seed ferns and conifers. In the shallow seas, ancient reef communities rose from the seafloor, surrounded by ecosystems that had been evolving for hundreds of millions of years. This was the late Permian, approximately 252 million years ago. It was an established complex world, approaching the most severe biological crisis in the history of complex life on Earth. More than two-thirds of marine animal genera disappeared, while species level estimates climb much higher. Ecosystems collapsed on land. Entire evolutionary lineages simply vanished from the fossil record. But this was not destruction delivered in a single instant. Enormous volcanic activity erupted across what is now Siberia, but the lava itself may not have been the greatest danger. Deep underground, magma pushed through carbon rich sediments, releasing gases that help transform the atmosphere, climate, and oceans. Temperatures climbed, forests collapsed, vast regions of seawater lost the oxygen complex life needed to survive, while toxic conditions spread through oceans already pushed toward their biological limits. And even after the main extinction pulse had passed, Earth remained unstable for millions of years. Yet among the survivors was something almost insignificant beside the giants that disappeared, a squat, pig-faced herbivore called Lystrosaurus. In the devastated world that followed, it would become one of the most successful vertebrates on the planet. In this video, we're uncovering how volcanic activity beneath Siberia became connected to collapsing forests, suffocating seas, vanished predators, and the unlikely survivors that inherited the ruins. But before we do, let me know in the comments. Are you listening to this to fall asleep, or you're here only for the knowledge? Let's go back to the world before the extinction, when Pangaea stretched across the planet and the ecosystems about to disappear were still very much alive. The Permian period marked the final chapter of the Paleozoic era, extending from about 299 million years ago until about 252 million years ago. Across that immense span, the drifting pieces of Earth's crust gradually gathered into a single supercontinent known as Pangaea. Its outline stretched from high northern latitudes through tropical regions and onward toward the far south, creating one uninterrupted expanse of land unlike anything living today has ever experienced. Surrounding this enormous continent was Panthalassa, a global ocean that occupied much of the planet's surface. Along the eastern margin of Pangaea lay the broad waters of the Tethys Ocean, where coastlines curved around warm shallows rich with marine life. Between these contrasting seas and the sprawling landmass stood countless environments shaped by distance, elevation, rainfall, and seasonal change. Geography became the quiet architect of every landscape, influencing where rivers wandered, where forests flourished, and where dry plains stretched toward distant horizons. A continent of such remarkable size behaved differently from smaller land masses. Moist air arriving from the surrounding oceans gradually lost much of its water before reaching the deep interior. Far from coastal influences, rainfall often became scarce, while seasonal contrasts grew stronger. Hot summers and cool winters could differ sharply, especially across broad inland basins where moderating ocean breezes never arrived. Dry regions expanded across many interior landscapes, forming belts of arid and semi-arid country that challenged the plants and animals living there. Even so, Pangaea cannot be imagined as one uninterrupted desert. Near the equator, conditions supported broad river systems, wetlands, and dense vegetation where water remained dependable. Temperate regions hosted forests, adapted to changing seasons, while higher latitudes experienced cooler climates with distinctive plant communities. Seed ferns, conifers, and many other forms of vegetation occupied habitats suited to local conditions. Life responded continuously to shifting rainfall, changing elevations, and differences in sunlight that varied from one latitude to another. Mountain ranges rose across parts of the supercontinent, guiding weather patterns and redirecting rivers toward inland basins or distant coastlines. Wide continental shelves bordered many shorelines before descending into deeper seas, providing productive marine habitats closely connected to life on land. Valleys, floodplains, and enclosed basins created countless ecological neighborhoods, each supporting its own collection of species shaped by local circumstances. Although animals could travel across connected land without crossing wide oceans, movement offered no guarantee of survival. Suitable climates did not extend evenly across Pangaea. Habitable regions formed broad belts that shifted with changing environmental conditions, compressing populations into narrower spaces whenever temperatures or rainfall drifted beyond familiar limits. A connected continent could still contain formidable barriers created by heat, drought, mountains, or expanding drylands. Even under these demanding conditions, the late Permian remained richly productive. Forests anchored food webs, rivers carried nutrients across fertile plains, and coastal waters supported thriving marine communities. The stage had already been assembled long before catastrophe arrived, filled with established ecosystems whose inhabitants had spent millions of years adapting to this singular world of one continent and one enormous ocean. Across the floodplains, forests, and shallow coastal waters of the late Permian, life had already settled into intricate relationships built over immense spans of time. Dinosaurs had not yet appeared. Their age remained far beyond the horizon. The dominant land animals belonged instead to lineages that filled nearly every ecological role, from towering herbivores to swift hunters, each shaped by countless generations adapting to the changing landscapes of Pangaea. Among the most important were the synapsids, a major branch of vertebrate life that would eventually give rise to mammals. During the Permian, however, these creatures fit comfortably into neither modern mammals nor reptiles as they are commonly understood today. They represented their own diverse collection of forms, carrying anatomical features unlike anything now roaming the planet. Their success reflected an evolutionary experiment already flourishing long before familiar mammals emerged. Large plant eaters wandered many of these environments, with Dicenodonts standing among the most widespread. Their heads ended in sturdy beak shaped jaws suited for cropping vegetation, while many species carried a pair of enlarged tusks projecting from the upper jaw. Some remained modest in size, browsing close to the ground, while others grew into imposing animals capable of traveling great distances in search of food. In several regions, parasaurs also occupied important grazing roles. These broad bodied herbivores, protected by thick, rugged skeletons, shared the landscape with many other therapsid plant eaters that consumed leaves, stems, and hardy seed plants. Predators moved through these communities with equal variety. Gorgonopsians ranked among the largest hunters of their time, recognizable by elongated skulls and powerful canine teeth that extended prominently from the mouth. Their limbs stood more upright than those of many earlier four-limbed vertebrates, allowing movement that balanced strength with increasing efficiency across open ground. Alongside them lived the Rosophalians, another successful predatory group, displaying a wide range of body sizes and hunting strategies. In wetlands and river systems, large amphibious predators waded along the water's edge, adding another layer to food webs that had developed over millions of years. The landscapes supporting these animals were equally diverse. Forests spread across many regions, filled with seed ferns and conifers that formed dense canopies where conditions allowed. Across southern Pangaea, Glossopteris vegetation covered broad areas, creating one of the defining plant communities of the age. Every habitat supported insects, smaller vertebrates, fungi, and countless organisms whose remains rarely dominate museum displays, but whose lives connected every level of the ecosystem. Marine environments displayed an equally rich complexity. Brachiopods blanketed portions of the seafloor beside bivalves, while relatives of ammonoids drifted through open waters. Crinoids anchored themselves where currents delivered food, and reef communities built by corals, sponges, algae, and microbial organisms created intricate habitats for many smaller creatures. Paleozoic seas followed patterns unfamiliar today. Brachiopods often held ecological importance, exceeding that of many shellfish familiar in modern oceans, while reef systems differed greatly from the coral dominated structures now found in tropical waters. These communities were neither early drafts nor unfinished versions of future ecosystems. They represented mature biological worlds, refined across hundreds of millions of years of evolution, where every species occupied a place shaped by long histories of adaptation. When extinction finally reached them, entire ecological roles disappeared alongside the animals themselves. Even as far to the north, geological forces were gathering strength within the rocks of what would become Siberia. Far to the north of the flourishing ecosystems spread across Pangaea, Earth's crust was entering an extraordinary chapter of its own history. Deep within the planet, molten rock accumulated in volumes so immense that the landscape would eventually record one of the greatest volcanic episodes ever recognized. Geologists describe such an event as a large igneous province, a region where exceptional quantities of magma reach or intrude Earth's crust during a geologically brief interval, leaving behind enormous bodies of solidified rock. This particular province is known today as the Siberian Traps, located across what is now northern Russia. The name does not refer to a dangerous place or hidden hazard. It comes from a Scandinavian word meaning steps, inspired by the staircase appearance, created when layer upon layer of hardened basalt forms broad terraces across the land. Even after hundreds of millions of years of erosion and burial, these stepped landscapes still hint at the unimaginable scale of the eruptions that once transformed the region. The original lava field extended across an enormous area, although its full size remains difficult to determine because later geological processes erased or concealed significant portions of it. Beneath younger sediments and weathered surfaces lies evidence that the total volume of magma reached millions of cubic miles. Few volcanic events in Earth's history approach such magnitude, making the Siberian Traps one of the largest known outpourings of molten rock ever preserved within the geological record. Even that description can create the wrong picture. This was not a solitary mountain rising above the landscape with one central crater. Instead, magma escaped through long fractures that opened across the crust, feeding repeated fissure eruptions over extended periods. Fresh lava spread across earlier flows, building immense sheets of basalt one after another. At the same time, large quantities of molten rock never reached the surface at all. They forced their way sideways through existing layers of rock, filling broad cracks and creating underground bodies called sills. A sill forms when magma is injected between older layers of rock instead of breaking directly upward. As the molten material spreads horizontally, it can extend for remarkable distances before cooling into solid stone. These hidden intrusions became every bit as important as the lava visible at the surface, although their significance would remain unknown until much later. Scientific investigation revealed their role. Careful dating has shown that major volcanic activity within the Siberian Traps began before marine life experienced its greatest losses. Establishing this sequence has required remarkable precision. Scientists compare radiometric ages obtained from volcanic minerals with dates preserved in sedimentary layers containing fossils from the extinction interval. Each improvement in dating techniques has refined the relationship between volcanic activity and biological collapse, bringing the timeline into sharper focus. One puzzle, nevertheless, remained. The earliest lava flows alone do not align perfectly with the most severe phase of extinction recorded in marine sediments. If surface eruptions had been the only driving force, the timing would be expected to match more closely. That mismatch encouraged researchers to examine the extensive underground network where magma continued advancing through older rocks, carrying heat into buried sedimentary layers, whose composition would prove far more consequential than the flowing lava visible above the surface. Much of the molten rock rising through northern Pangaea never burst into open air. Instead, enormous volumes spread through the crust, advancing sideways between older layers of stone where they remained concealed from the surface. These underground intrusions reached extensive sedimentary basins, including the Tunguska Basin, where the rocks preserved the remains of environments that had formed across immense stretches of geological time. Those buried layers contained an unusual mixture of materials. Thick coal deposits rested beside rocks rich in organic matter left behind by long vanished ecosystems. Carbonates recorded the accumulation of ancient marine sediments. Evaporites marked places where mineral rich waters had gradually dried away, while hydrocarbons remained trapped within porous formations. As magma entered this varied landscape, it encountered far more than ordinary stone. Every intrusion introduced intense heat into rocks filled with compounds capable of changing dramatically when temperatures rose. Geologists describe this process as contact metamorphism. In simple terms, hot magma heats the surrounding rocks until their minerals and chemical compounds begin to transform. The rock does not need to melt completely. Heat alone can alter its composition, breaking apart complex organic material and releasing gases that had remained locked away for millions of years. The underground environment became an immense chemical laboratory, operating across remarkable distances wherever expanding sills encountered suitable sediments. As these buried rocks baked under rising temperatures, they likely released substantial quantities of carbon dioxide together with methane, sulfur-bearing compounds, and gases containing halogens. Researchers also propose that pressure built within some heated regions until fractures opened toward the surface, creating explosive gas vents capable of carrying these materials into the atmosphere. Such eruptions may have resembled towering vents of steam, ash, and gas emerging far from the lava fields themselves, connecting deep underground reactions with the world above. Scientists refer to gases generated by heating sedimentary rocks as thermogenic carbon. This distinction matters because volcanic gases originated directly from magma, while thermogenic gases formed when magma transferred heat into surrounding sediments rich in carbon. Both sources may have contributed to the environmental crisis, although determining their exact proportions remains an active area of research. The available evidence points toward a combination of processes working together instead of one isolated mechanism acting alone. Support for this interpretation comes from several independent lines of evidence: high precision dating places, widespread sill emplacement, remarkably close to the interval when extinction intensified. The architecture of intrusive rock bodies shows that magma spread extensively through sedimentary basins, exactly where carbon rich rocks were abundant. Geochemical studies reveal unusual mercury and nickel anomalies preserved within extinction. Age sediments found far from Siberia, suggesting widespread dispersal of materials associated with volcanic activity. Carbon isotopes provide another important clue. Carbon from different sources contains slightly different proportions of its naturally occurring isotopes. When large amounts of carbon enter the atmosphere and oceans over a relatively brief geological interval, those changing proportions become recorded within rocks forming around the world. During the end of the Permian, scientists observe a pronounced negative carbon isotope excursion, signaling a rapid disruption of the global carbon cycle, consistent with an extraordinary release of carbon from multiple sources. Researchers do not claim to know the precise volume of gas released during this episode, and the calculations continue to improve as new evidence emerges. Even so, the broader picture has become increasingly clear. The significance of the Siberian event extended well beyond widespread basalt flows. Powerful chemical changes unfolded beneath the surface, sending their influence outward through the atmosphere and oceans as Earth's carbon cycle entered one of the most profound disturbances in its history. Every living thing, every ocean, every layer of rock, and every breath of the atmosphere participates in a continuous exchange of carbon. This movement, known as the carbon cycle, transfers carbon among living organisms, the air, the oceans, and Earth's crust over timescales ranging from days to millions of years. Under ordinary conditions, these pathways remain balanced, with carbon entering and leaving each reservoir at rates that ecosystems can gradually accommodate. That balance becomes increasingly difficult to maintain when carbon dioxide enters the atmosphere faster than natural processes can remove it. Volcanoes have always contributed carbon dioxide to Earth's atmosphere, while weathering of rocks, burial of organic material, and absorption by the oceans slowly return much of that carbon to long-term storage. During the end of the Permian, repeated volcanic activity and additional underground gas generation appear to have overwhelmed those slower processes, allowing carbon dioxide to accumulate across the planet. The warming that followed depended upon a familiar physical process known as the greenhouse effect. Certain gases within the atmosphere absorb part of the heat that Earth radiates back towards space after sunlight warms the surface. They then release that energy in many directions, slowing the overall escape of heat into space. Carbon dioxide does not act like a solid roof, trapping warmth beneath it. Instead, it changes the balance between incoming solar energy and outgoing heat, allowing the planet to retain more energy than before. Evidence suggests this transformation did not result from one enormous burst of gas released at a single moment. Carbon entered the Earth system through repeated pulses spread across an extended interval. Each episode added another contribution before earlier disturbances had fully subsided. This pattern allowed environmental pressures to accumulate progressively, placing increasing strain upon climates, oceans, and ecosystems already adapting to previous changes. One of the clearest geological records of this disruption appears as a pronounced negative carbon isotope excursion. Rocks preserving sediments from the end of the Permian contain a distinctive shift in the proportions of naturally occurring carbon isotopes. Remarkably, the same signal emerges in sedimentary sections separated by great distances across the globe. Marine basins and continental environments record comparable changes despite forming in widely different settings. That worldwide consistency carries profound importance. If identical carbon isotope patterns appear across distant regions, the underlying disturbance cannot be explained as an isolated regional event. The changing chemistry reached far beyond Siberia, affecting the atmosphere and oceans on a planetary scale. Geological layers, separated by thousands of miles, preserve matching evidence that Earth's carbon cycle had entered an exceptional period of instability. The principal phase of marine extinction unfolded rapidly in geological terms, according to high resolution records preserved beneath ancient seas. Even so, rapid within geology can still represent thousands or even tens of thousands of years. Conditions on land may have deteriorated through a somewhat longer and more complicated sequence, with different environments responding according to local geography and ecological resilience. Individual organisms often withstand modest environmental shifts during their own lifetimes. Populations survive only when enough individuals continue reproducing successfully, while species persist only if suitable habitats remain available and changing climates allow ranges to adjust. Environmental transformation occurring across comparatively brief geological intervals can outpace these slower biological responses. As warming altered rainfall patterns, influenced ocean circulation, and weakened ecosystems that stored carbon, each change reinforced the next, carrying Earth's climate toward the increasingly warmer conditions recorded across the boundary between the Permian and the Triassic. The rocks left behind by the end of the Permian preserve more than fossils. They also preserve chemical signatures that reveal how the climate itself changed. Scientists call these preserved clues climate proxies, physical or chemical indicators that allow ancient environmental conditions to be estimated long after the original world has disappeared. Because no thermometer survived from the Permian, these natural records have become the closest witnesses to the temperatures that once shaped life across the planet. Among the most valuable climate proxies are oxygen isotope measurements obtained from carefully preserved fossil materials. The proportion of naturally occurring oxygen isotopes incorporated into shells and other mineralized remains changes according to the temperature of the water in which those organisms lived. By comparing these chemical patterns across many locations, researchers have reconstructed a picture of remarkable global warming. Some reconstructions indicate that average planetary temperatures rose by more than 18 degrees Fahrenheit during the crisis, although the precise magnitude and regional differences continue to be refined through ongoing study. A global average does not mean every landscape warmed by exactly the same amount. Oceans responded differently from continents because water absorbs and releases heat more gradually than land. Deep within Pangaea, where the influence of surrounding seas was already limited, seasonal contrasts could become especially severe. Tropical regions faced another challenge. Even modest increases above already warm conditions can push complex animals closer to the limits of their physiology, leaving far less room for additional warming before survival becomes increasingly difficult. Heat affects living organisms in many interconnected ways. Water escapes from bodies more rapidly, increasing the risk of dehydration wherever fresh supplies become scarce. Activity often shifts toward shorter periods when temperatures become less demanding, reducing the time available for feeding, growth, and reproduction. Internal metabolism also requires greater effort as organisms attempt to maintain essential biological processes. Developing embryos may prove especially vulnerable because successful growth depends upon environmental conditions remaining within relatively narrow limits. Plants faced their own constraints. Photosynthesis operates efficiently only across particular ranges of temperature and water availability. As conditions became hotter, the process grew increasingly difficult wherever moisture also declined. Leaves lost water more rapidly, soils dried more readily, and prolonged drought added another layer of stress. A forest could remain standing while its ability to grow, reproduce, and recover steadily weakened beneath changing climatic conditions. Animals whose body temperatures depend strongly upon their surroundings encountered additional obstacles. These ectothermic creatures could retreat into shade, burrows, or nearby water to reduce thermal stress, yet those refuges offered protection only while they remained cool and well supplied with moisture. As warming continued, dependable shelter became harder to find. Habitats that once buffered daily extremes gradually lost much of their protective value. Rising temperatures also accelerated evaporation from soils, lakes, wetlands, and shallow waters. Regions already prone to limited rainfall experienced growing water shortages as evaporation removed moisture faster than it could be replaced. Dry landscapes expanded, vegetation declined, and the connections linking plants, animals, and freshwater sources became increasingly fragile. Temperature, therefore, represented far more than a changing atmospheric measurement. It reshaped every ecological relationship, influencing where species could survive, how food webs functioned, how water moved across the landscape, and how ecosystems stored carbon. As these transformations unfolded together, the stability of seasonal rainfall and long established weather patterns also began to weaken, carrying the climate into an even more unpredictable state. Climate does not depend only upon average temperatures. It also depends upon the rhythm of changing seasons, recurring rainfall, and familiar patterns that living organisms gradually adapt to across countless generations. New research suggests that, during the closing chapter of the Permian, those dependable rhythms may have weakened as the warming planet entered a prolonged period of unusual climatic instability. One proposed contributor resembles the modern phenomenon known as El Niño. El Niño is a reorganization of tropical Pacific heat and atmospheric circulation that alters weather patterns far beyond the ocean where it begins. The late Permian world, however, did not possess an ocean basin identical to today's Pacific Ocean. When scientists describe the ancient climate as El Niño-like, they are referring to comparable atmospheric and oceanic behavior rather than suggesting a perfect copy of the modern system. Climate models, combined with evidence preserved in geological records, indicate that exceptionally persistent El Niño-like conditions may have developed as greenhouse warming intensified. These circulation changes appear to have interacted with the already warming climate, altering rainfall across enormous regions. The result was a world where familiar weather patterns became increasingly unreliable, placing additional pressure upon ecosystems that had already begun responding to rising temperatures. Many species can survive if environmental conditions shift gradually toward a new average. Recovery becomes far more difficult when conditions swing repeatedly between extremes before populations have time to adjust. A favorable season may allow partial recovery, only to be followed by severe drought, destructive flooding, or another abrupt change that erases those gains. Repeated instability steadily weakens ecosystems, even if individual events remain survivable on their own. Some regions likely experienced prolonged, dry conditions that reduced rivers, wetlands, and soil moisture. Elsewhere, unusually intense rainfall may have stripped vegetation, flooded lowlands, and carried sediments into lakes and coastal waters. Growing seasons became less dependable as rainfall arrived at unfamiliar times or failed altogether. Plants damaged repeatedly by alternating extremes, struggled to rebuild healthy communities before the next climatic disruption arrived. Seasonal predictability supports nearly every ecological relationship. Plants, time growth, flowering, and reproduction according to recurring environmental signals. Herbivorous animals depend upon reliable periods when fresh vegetation becomes available. Freshwater ecosystems also follow seasonal cycles, with changing water levels shaping breeding, migration, and feeding opportunities for many aquatic organisms. When those recurring patterns become increasingly erratic, disruptions spread outward through entire food webs. Researchers have proposed that persistent mega El Nino conditions may have contributed to widespread deforestation by placing repeated stress upon forests already weakened by heat and water shortages. Reef communities could also have suffered as changing temperatures and shifting ocean conditions altered habitats, supporting countless marine organisms. Plankton populations, forming the foundation of marine food chains, may likewise have experienced repeated disturbances that echoed upward through larger ocean ecosystems. This developing hypothesis does not replace the central importance of Siberian volcanism. Instead, it adds another layer to an increasingly detailed picture of the extinction. Volcanic emissions introduced extraordinary quantities of carbon into the Earth system. That carbon forced planetary warming, rising temperatures then disrupted atmospheric circulation and ocean dynamics, allowing climatic instability to multiply ecological stress across land and sea. As environmental conditions grew less predictable, forests faced mounting challenges beyond heat alone. The vegetation covering Pangaea no longer responded merely to warmer temperatures. It also confronted repeated swings in rainfall, changing seasons, and increasingly unreliable water supplies, making Earth's plant communities one of the first great foundations of the terrestrial world to begin unraveling. Long before the first animal collapsed from hunger or thirst, the transformation had already begun among the plants that shaped the land itself. Forests were more than collections of trees. They formed living systems that connected soil, water, climate, and countless organisms into stable communities that had developed across millions of years. As environmental pressures accumulated, those communities gradually lost the resilience that had once allowed them to recover from ordinary disturbances. Across the southern regions of Pangaea, broad landscapes were dominated by the seed fern known as Glossopteris. Elsewhere, conifers and many other seed plants occupied environments suited to different patterns of rainfall, temperature, and seasonality. Each major vegetation community reflected the climate in which it had evolved. Plants had adapted to particular ecological zones, creating forests that differed from one region to another, while together supporting nearly every terrestrial ecosystem on Earth. Their importance extended far beyond feeding herbivores. Root systems anchored soil against erosion while helping rainwater soak into the ground instead of flowing rapidly away. Leaves and branches reduced direct sunlight, reaching the surface, moderating local temperatures, and slowing water loss. Forests created shelter for countless organisms, from insects to large vertebrates, while storing substantial amounts of carbon within living tissues and accumulating organic material in soils and wetlands. Their influence reached nearly every part of the terrestrial environment. One of the clearest geological signs of disruption appears in what researchers call the coal gap. Across a lengthy interval spanning the boundary between the Permian and the Triassic, evidence for extensive peat-forming wetlands becomes remarkably scarce. This does not mean vegetation disappeared everywhere across the globe. Rather, it indicates that ecosystems capable of producing and preserving thick peat deposits had been profoundly disrupted. Wetland forests that had persisted through long stretches of geological history were no longer functioning in the same way. Microscopic evidence supports this picture of widespread ecological turnover. Pollen and spores preserved within sedimentary rocks record major changes in plant communities across the extinction interval. Species that had dominated many landscapes declined, while different groups became increasingly common after disturbance. Some boundary sections also contain unusually abundant fungal spores. These were once interpreted as evidence that enormous quantities of dead wood covered the landscape, providing food for decomposing fungi. Today, scientists recognize that the ecological meaning of this fungal signal remains under active debate, and several explanations continue to be investigated. Forest communities were likely responding to repeated stresses acting together instead of one isolated cause. Higher temperatures increased physiological strain, drought reduced available moisture, rainfall became increasingly unpredictable. Acid deposition generated from atmospheric chemical changes may have damaged leaves and soils in some regions. Geological evidence also indicates that wildfires occurred across portions of the landscape, adding another source of disturbance where dry vegetation became more susceptible to burning. A landscape could still appear green while undergoing profound ecological decline. Mature forests depend upon large trees, continuous canopies, deep root systems, and diverse plant communities that reinforce one another over long periods. When repeated disturbances interrupt that stability, fast-growing opportunistic plants often expand into newly opened ground. Vegetation remains present, yet it no longer performs the same ecological roles with equal effectiveness. The terrestrial world therefore shifted from persistent forest communities toward landscapes repeatedly interrupted before full recovery could occur. As protective vegetation weakened, the living foundation supporting soils also began to loosen, exposing the ground itself to the next stage of the unfolding crisis. The ground beneath a forest is never merely loose earth. It is a woven structure held together by countless living roots that spread through the soil in every direction. Fine rootlets grip tiny particles, while larger roots anchor entire slopes against gravity. Above them, leaves, fallen branches, and low vegetation soften the impact of falling rain, allowing water to soak gradually into the ground instead of racing across the surface. Healthy landscapes lose soil only slowly because living plants continually protect the land that supports them. As forests became increasingly disrupted, those natural defenses weakened, bare patches expanded where mature vegetation failed to recover after repeated environmental stress. Exposed soil dried beneath stronger heat, losing moisture that had once helped hold particles together. Without extensive root networks, sediments became easier for wind and flowing water to carry away. Riverbanks that had remained stable for long intervals began changing more frequently as loose material entered streams from surrounding hills and plains. Sedimentary rocks formed across the boundary between the Permian and the Triassic preserve evidence of this growing instability. Many regions contain thicker deposits of coarse sediment than earlier landscapes produced, indicating accelerated erosion on land. River systems also changed their character. Instead of following relatively stable courses bordered by well-established floodplains, some rivers developed braided channels that divided repeatedly before joining again farther downstream. Braided rivers reveal much about the conditions that created them. Rather than flowing within one dependable channel, water spreads across numerous shifting pathways, separated by temporary bars of sand and gravel. Such rivers usually form where large quantities of loose sediment arrive faster than the current can carry it away. Their banks remain comparatively unstable because fresh deposits are continually rearranged as water changes course across the valley floor. Alternating drought and intense rainfall likely accelerated this transformation. Dry periods weakened vegetation while hardening exposed surfaces. When powerful storms finally arrived, rainwater could rush rapidly across the landscape instead of sinking into the soil. Hillsides, stream banks, and open plains surrendered enormous quantities of sediment during relatively brief intervals, carrying material toward larger rivers that ultimately delivered it into coastal waters. At the same time, another process continued reshaping the continents. Chemical weathering gradually breaks down rocks through reactions involving warmth, water, and naturally occurring acids. As temperatures remained elevated and rainfall patterns shifted, weathering released increasing amounts of dissolved elements from exposed rock and soil. Rivers transported phosphorus, nitrogen bearing compounds, iron, and many other minerals toward the oceans together with suspended sediment. This created a crisis that moved in two directions at once. On land, fertile soils accumulated over immense spans of time disappeared more rapidly than they could be replaced. Productive ecosystems lost the foundation needed to support recovering vegetation. Offshore, the same rivers delivered excessive nutrients and sediment into shallow marine environments already coping with changing climate and ocean chemistry. Clouds of suspended sediment reduced the sunlight, reaching underwater habitats where many organisms depended upon clear conditions for growth. Fine particles settled across the seafloor, covering communities adapted to firmer substrates and altering coastal environments that had remained comparatively stable for long intervals. Habitats supporting diverse marine life gradually became less suitable as river-borne material accumulated across continental margins. Erosion therefore became more than a consequence of environmental disruption. It acted as a continuing amplifier. Even after the earliest pulses of carbon had entered the Earth system, damaged landscapes continued transferring sediment and dissolved nutrients into the seas, extending ecological stress through natural processes that no longer operated within their former balance. Across both land and water, the resources sustaining animal life steadily diminished as food and habitat began disappearing together. For many plant-eating animals, survival depended upon a landscape that offered dependable abundance through changing seasons. A hillside covered with vegetation did not necessarily provide enough nourishment to sustain large bodies, growing young, and future generations. As the stability of plant communities weakened, the first signs of ecological collapse reached the animals that relied upon them every day, often long before entire species disappeared from the fossil record. Among the most familiar herbivores of the late Permian were the dicynodonts, sturdy relatives of mammals whose broad beaks gathered vegetation from floodplains, woodlands, and open habitats. They shared the landscape with many other plant-eating reptiles and synapsids, each adapted to particular foods and environments. Their survival depended upon far more than the simple presence of green plants. Healthy populations required large quantities of edible vegetation, nutritious new growth, reliable fresh water, and places where young could mature with reasonable safety from environmental extremes. Plants living under prolonged heat and drought changed in ways that reduced their value as food. Water became scarcer within leaves and stems as vegetation struggled to conserve moisture. Fresh growth slowed considerably, leaving more older tissue that was tougher to chew and digest. Many stressed plants also altered the chemical compounds they produced, increasing natural defenses that discouraged grazing. A hillside might continue supporting vegetation while offering much less nourishment than before. Large herbivores proved especially vulnerable to these changes. Their bodies required substantial amounts of food every day simply to maintain normal activity. Reproduction also proceeded gradually, with relatively few offspring surviving to adulthood under favorable conditions. Expanding into larger territories offered only limited protection when productive habitats declined across entire regions. Walking greater distances demanded additional energy, while exposing animals to landscapes where food and water had become increasingly unreliable. Population decline rarely unfolded all at once. Juvenile animals often suffered first because growing bodies tolerate shortages less effectively than mature individuals. Adults experiencing nutritional stress could postpone reproduction until conditions improved, reducing the number of young entering the population. Herds gradually became smaller as mortality exceeded successful births. Once populations became scattered into isolated groups, local extinction became increasingly likely whenever another drought or failed growing season struck before recovery could begin. Remaining rivers and productive floodplains grew increasingly important as surrounding environments deteriorated. Herbivores concentrated wherever water remained available, and vegetation continued growing for longer portions of the year. Such gathering places supported life, yet they also increased competition for limited resources. Food disappeared more rapidly as larger numbers of animals relied upon shrinking areas capable of sustaining them. Many species probably attempted to follow shifting belts of vegetation as climates changed across Pangaea. Some populations succeeded in expanding into newly favorable regions, helped by the remarkable connectedness of the supercontinent. Others encountered barriers that proved far more difficult to cross. Mountain ranges redirected movement, broad deserts separated productive habitats, and extensive zones of oppressive heat limited travel across otherwise open landscapes. Opportunity and confinement existed side by side, producing different outcomes from one region to another. This unfolding crisis, therefore, did not resemble one simultaneous global famine. Some environments deteriorated earlier, while others retained productive ecosystems for longer intervals. Local geography, water availability, and regional climate all influenced how rapidly herbivore communities declined. Even so, as fewer plant eaters survived, less energy flowed upward through terrestrial food webs. The living bridge connecting vegetation to larger carnivores steadily weakened, leaving predators increasingly dependent upon prey that had become progressively harder to find. No animal stood farther from the green foundation of the landscape than its greatest hunters. Their strength depended upon every living level beneath them remaining connected, from the smallest plants drawing energy from sunlight to the largest herbivores roaming the floodplains. Once those lower layers weakened, the highest predators inherited consequences they could neither prevent nor escape. Among the dominant hunters of many late Permian ecosystems were the Gorgonopsians. These formidable synapsids occupied the role later filled by large mammalian and reptilian carnivores in younger worlds. Their skulls contained unusually large temporal openings that created space for powerful jaw muscles, allowing exceptionally forceful bites. Long canine teeth projected beyond the mouth, giving several species a striking saber-toothed appearance. Some forms also possessed relatively upright limbs, enabling more efficient movement than the sprawling posture common among many earlier terrestrial vertebrates. Those impressive canine teeth often invite comparisons with the famous saber-toothed cats that appeared much later. The resemblance, however, reflects convergent evolution rather than close relationship. Different groups can independently evolve similar anatomical solutions when facing comparable ecological challenges. Gorgonopsians and saber-toothed cats belonged to separate evolutionary branches divided by immense spans of geological time, yet both developed elongated canine teeth suited for dispatching large prey. The position of these predators within the food web also carried unavoidable limitations. Ecologists describe this arrangement as a trophic pyramid. Plants capture energy from sunlight and support herbivores. Herbivores, in turn, sustain carnivores. At each successive level, only part of the available energy passes upward because much is used for movement, growth, body maintenance, and reproduction. As a result, every ecosystem naturally supports far fewer top predators than plant eaters. Smaller populations bring their own vulnerabilities. When habitats become fragmented, isolated predator groups may struggle to find mates or maintain healthy genetic diversity. Reproductive success becomes increasingly uncertain as individuals occupy larger distances from one another. Population recovery also proceeds more gradually because relatively few young are produced compared with the enormous numbers of plants and smaller animals forming the lower levels of the ecological pyramid. Specialization added another challenge. Many large gorgonopsians were adapted to hunting sizable herbivores, capable of providing substantial nourishment from each successful pursuit. A landscape increasingly dominated by scattered, opportunistic animals offered a very different resource. Anatomical adaptations perfected for overpowering large prey could become less effective when only much smaller animals remained abundant. Scavenging probably provided temporary opportunities as environmental pressures increased. Carcasses left by drought, disease, or starvation represented valuable sources of food whenever they became available. Such resources, however, appeared unpredictably and disappeared quickly as competing scavengers arrived. A breeding population cannot rely indefinitely upon occasional carcasses because successful reproduction requires dependable nourishment across many seasons. Fossil evidence indicates that the great Gorgonopsians disappeared near the extinction interval, although the pattern on land appears more extended than the abrupt marine losses recorded elsewhere. Much of this understanding comes from South Africa's Karoo Basin, where an unusually continuous sequence of sedimentary rocks preserves changing vertebrate communities across a long stretch of geological time. Because successive fossil assemblages remain stacked within these rock layers, scientists can trace disappearances, surviving lineages, and eventual replacements with uncommon detail. The Karoo record suggests that terrestrial vertebrate communities changed across an interval that may have lasted roughly 1 million years, allowing decline and replacement to unfold through multiple ecological stages instead of one instantaneous collapse. Long before the last Gorgonopsian vanished from the fossil record, the ecological role it had mastered was already fading, leaving one of the Permian's greatest hunters alive in body for a time, yet increasingly without the world that had shaped its existence. As the surrounding landscape became increasingly difficult to inhabit, strips of water crossing the continents acquired new importance. Rivers, marshes, oxbow lakes, and wetlands formed narrow corridors where life could persist longer than in many upland environments. These freshwater systems did not escape the broader environmental crisis, yet for a time they offered conditions that remained more favorable than the drying terrain beyond their banks. Water itself provided the most immediate advantage. Animals gathered where dependable drinking sources still existed, reducing the risk of dehydration during prolonged heat. Nearby vegetation often remained greener because soils retained moisture for longer periods, supplying food after surrounding plant communities had declined. The damp ground along river margins also created softer sediment where many animals could rest, dig, or shelter from the hottest portions of the day. Air temperatures close to water frequently remained somewhat lower than across exposed plains, producing localized environments where physiological stress could be reduced. Late Permian freshwater habitats supported remarkably diverse communities. Large amphibians occupied rivers and wetlands alongside numerous fish adapted to flowing or still waters. Small reptiles and synapsids searched the margins for food, while countless invertebrates inhabited mud, submerged vegetation, and shallow pools. These interconnected communities recycled nutrients and transferred energy between aquatic and terrestrial ecosystems, making freshwater environments disproportionately important compared with their relatively limited geographic extent. Among these inhabitants, amphibians remained especially dependent upon water. Many possessed permeable skin that lost moisture readily under hot, dry conditions. Reproduction frequently required aquatic environments where eggs and developing young remained protected from desiccation. Even adults capable of spending time on land generally relied upon nearby water to complete their life cycles. As drought intensified elsewhere, rivers and wetlands became increasingly essential for their survival. Refuge, however, carried its own difficulties. Shrinking freshwater habitats concentrated growing numbers of animals into progressively smaller areas. Competition for food, breeding sites, and shelter intensified as populations overlapped more frequently. Close contact also created favorable conditions for parasites and infectious diseases to spread through crowded communities, placing additional pressure upon species already coping with environmental stress. Persistent drought gradually altered the water itself. River channels became shallower. Isolated pools formed where continuous flow had once existed, and wetlands contracted. Reduced circulation lowered the amount of dissolved oxygen available for aquatic organisms. Warm water naturally holds less oxygen than cooler water, leaving fish and many invertebrates increasingly vulnerable whenever temperatures remained elevated for extended periods. Sediment washing from damaged landscapes added further complications. Fine particles settled across stream beds, burying eggs deposited among gravel or vegetation. Suspended material passed through the delicate gills of aquatic animals while also reducing water clarity. Feeding became more difficult as visibility declined, and changing sediments transformed habitats that many organisms had occupied for generations. When heavy rainfall finally arrived after prolonged dry intervals, the same rivers sustaining life could become agents of destruction. Vegetation no longer slowed runoff effectively across many watersheds, allowing sudden floods to surge through valleys carrying enormous quantities of water, mud, and debris. Sheltered pools disappeared beneath fast-moving currents, and established refuges could be swept away within remarkably short periods. Some animals increased their chances of survival by retreating underground. Burrows buffered changing temperatures, preserved higher humidity, and offered protection from passing wildfires or harsh surface conditions. Even so, underground shelter alone could not guarantee survival. Food still needed to be found, and dependable water remained indispensable. Freshwater corridors continued guiding adaptable species through transformed landscapes, connecting scattered habitats as the atmosphere introduced still more challenges across the recovering world. The air itself began carrying traces of the upheaval unfolding across the continents. Long after volcanic eruptions faded beyond the horizon, particles released into the atmosphere continued traveling across immense distances before settling upon forests, lakes, rivers, and shallow seas. These materials did not create the extinction by themselves, yet they added new pressures to ecosystems already struggling under persistent warming, changing rainfall, and widespread habitat disruption. Evidence preserved near the boundary between the Permian and the Triassic indicates that fires occurred repeatedly in several regions. Thin layers containing charcoal and soot record episodes of combustion that affected ancient landscapes. Wildfire may have become more common where prolonged heat dried vegetation and left forests increasingly vulnerable to ignition. Lightning striking parched woodlands could have started some fires, while volcanic activity supplied additional opportunities through hot eruptive material and heated gases capable of igniting combustible organic matter. Researchers have also proposed the presence of coal fly ash within certain geological deposits associated with the Siberian eruptions. Coal fly ash differs from ordinary charcoal produced by burning vegetation. When underground coal deposits ignite or become heated during volcanic activity, combustion can generate fine particles containing metals and chemically complex materials that differ from those created during a typical forest fire. The distribution and significance of these deposits continue to be investigated, yet they offer another possible connection between volcanism and changing environmental conditions. Another important signal appears in the form of mercury preserved within sedimentary rocks. Unusually elevated mercury concentrations occur across many sections, spanning the extinction interval, and are widely interpreted as evidence for extensive volcanic influence. Mercury released into the atmosphere during prolonged eruptions could travel great distances before settling onto land and into water. Although mercury alone does not explain the biological crisis, its widespread occurrence provides another marker linking environmental disruption to repeated volcanic activity. Volcanoes released more than carbon dioxide. They also emitted substantial quantities of sulfur dioxide. Once present in the atmosphere, sulfur dioxide could form tiny aerosol particles capable of reflecting part of the incoming sunlight back into space. Such aerosols may have produced intervals of temporary cooling even while the broader climate continued warming. Sulfur compounds also contributed to acid deposition as they returned to Earth's surface through rainfall and other forms of precipitation, placing additional stress upon soils, freshwater systems, and vegetation. The contrasting lifetimes of these volcanic emissions shaped their influence upon the planet. Sulfur aerosols generally remained in the atmosphere for comparatively brief periods before settling out. Carbon dioxide behaved very differently. It persisted far longer, allowing repeated volcanic pulses to build a prolonged greenhouse effect that outlasted the cooling influence of individual sulfur-rich eruptions. Short-lived fluctuations therefore unfolded against a steadily warming background that continued evolving over extended intervals. Scientists have also explored the possibility that volcanic gases containing halogen elements affected the protective ozone layer high within the atmosphere. If ozone became depleted in some regions, increased ultraviolet radiation could have reached Earth's surface. Certain fossil pollen grains display unusual abnormalities that some researchers interpret as evidence of ultraviolet stress affecting reproductive tissues in ancient plants. The scale of any ozone depletion, however, remains uncertain, and its overall biological importance continues to be debated. Current evidence does not support the idea that the atmosphere became uniformly poisonous across the entire planet. Instead, wildfire, sulfur related acidification, mercury deposition, possible ozone disruption, and repeated volcanic emissions are best understood as additional burdens acting upon organisms already weakened by rising temperatures and collapsing habitats. While these pressures reshaped life on land, an even broader transformation was unfolding across the oceans, where the greatest losses of the extinction were about to emerge. Far beyond the changing shorelines, another transformation unfolded within the water itself. Every ocean depends upon a delicate balance between the atmosphere above and the immense depths below. That balance had supported marine life for countless generations, allowing oxygen to reach habitats stretching from sunlit coastal shelves to the darkest parts of the seafloor. As the climate continued changing, this exchange became steadily less effective. Marine animals cannot obtain oxygen by separating it from water molecules. Instead, they depend upon dissolved oxygen, tiny oxygen molecules already mixed within the surrounding water. Fish absorb this dissolved oxygen through their gills, while countless invertebrates draw it across delicate tissues adapted for underwater respiration. Even animals buried within seafloor sediment ultimately rely upon oxygen that first entered the ocean through natural exchange with the atmosphere or through photosynthesis carried out by microscopic organisms and marine plants living near the surface. The amount of dissolved oxygen that seawater can hold depends strongly upon temperature. Cooler water generally retains more dissolved gas, while warmer water releases it more readily. As surface oceans became warmer, the available supply of dissolved oxygen naturally declined. This reduction alone created additional pressure for marine organisms whose survival depended upon extracting enough oxygen from every passing current. Ocean circulation normally helps replenish deeper environments. Winds and currents move surface waters across great distances, while colder, denser water sinks in certain regions and gradually carries oxygen into the deep ocean. Over long intervals, this circulation renews water that would otherwise become depleted as animals, microorganisms, and chemical reactions consume available oxygen. Persistent warming weakened part of this natural system by increasing stratification. Stratification describes the formation of stable water layers that resist mixing with one another. Warm surface water remained above colder, denser water lying farther below. Because the upper layer became more buoyant, vertical exchange slowed. Oxygen, entering from the atmosphere or produced through photosynthesis, remained concentrated near the surface instead of being transported efficiently into deeper habitats. The challenge was especially important within Panthalassa, the immense ocean covering most of the planet during the late Permian. Its extraordinary size and depth make its history difficult to reconstruct today because nearly all of its original seafloor has disappeared through plate tectonics. Most surviving evidence, therefore, comes from sediments that accumulated along continental shelves and shallow marine margins, where rocks escaped destruction and preserved fossils together with valuable chemical signatures. Those preserved rocks reveal an important distinction. Some marine basins naturally develop low oxygen conditions because restricted circulation prevents efficient renewal. Such local environments existed long before the extinction interval. Evidence from many continental shelf deposits, however, indicates that oxygen loss expanded well beyond isolated basins during this crisis, affecting broad portions of the marine realm, even though conditions remained different from one region to another. Scientists investigate these changing conditions using redox proxies, chemical indicators preserved within ancient sediments that reveal whether seawater contained abundant oxygen or existed under oxygen, poor conditions when the rocks formed. These indicators show that deoxygenation did not spread everywhere at the same pace. Different ocean basins, water depths, and continental margins crossed critical thresholds during different stages of the environmental upheaval. For marine animals, warming and oxygen loss reinforced one another. Rising temperatures increased metabolic demand, causing organisms to require more oxygen precisely when less dissolved oxygen remained available. Habitats that had supported thriving communities gradually approached biological limits. Across many continental shelves, another influence was arriving as rivers carried growing amounts of sediment and dissolved nutrients from the increasingly unstable continents into an ocean already struggling to breathe. Along many continental margins, rivers carried more than water. Every current arriving from the land transported dissolved minerals, fine sediment, and fragments of organic material gathered across thousands of miles. These deliveries had always linked continents with the sea, supplying ingredients that sustained marine life. As landscapes became increasingly unstable, however, the balance of those exchanges began to shift in ways that favored abundance at first, followed by growing ecological strain. The growth of microscopic marine organisms depends upon more than sunlight and water. Plankton require essential nutrients to build new cells, reproduce, and support the wider marine food web. Among the most important are phosphorus and nitrogen, elements that naturally limit biological production when present only in modest quantities. In many coastal environments, the availability of these nutrients determines how much microscopic life can flourish at any given time. As rivers drained increasingly eroded landscapes, larger amounts of dissolved nutrients entered shallow coastal seas. Material released from weathered rocks and transported from damaged soils reached continental shelves directly, where currents distributed these compounds through surface waters. Areas that had once experienced relatively balanced nutrient supplies could temporarily support greater biological productivity as these new inputs accumulated. This process is known as eutrophication, a condition in which excess nutrients stimulate rapid biological growth that is later followed by oxygen-consuming decay. The sequence unfolds gradually. Nutrients first become available to microscopic organisms suspended near the surface. Plankton and many microbes multiply in response to the improved supply. Their populations eventually decline as cells die naturally or are consumed by other organisms. Dead organic matter then sinks toward deeper water, where decomposer microbes begin breaking it apart. That decomposition requires oxygen, steadily drawing dissolved oxygen from the surrounding water. Because these events occur at different depths, the surface, ocean, and deeper environments can experience very different conditions at the same time. Sunlit surface waters may continue supporting productive communities while oxygen becomes increasingly scarce farther below. A thriving upper layer, therefore, does not necessarily indicate a healthy marine ecosystem from top to bottom. Organisms living near the seafloor can encounter severe oxygen shortages even while microscopic life remains plentiful closer to the surface. Continental shelves proved especially important during this interval because they supported exceptional biological diversity while also receiving the greatest amount of runoff from nearby land. Countless animals depended upon these productive coastal habitats for feeding, reproduction, and early development. At the same time, suspended sediment carried by rivers reduced the penetration of sunlight through the water. Lower light levels limited photosynthesis in some locations, placing additional pressure upon organisms that relied upon clear, illuminated conditions. As oxygen declined, microbial communities also began changing. Different groups of microorganisms prosper under oxygen poor conditions than those favored in well oxygenated waters. These shifts influenced how nutrients were recycled within marine sediments and the surrounding water. In some environments, reduced oxygen allowed nutrients to return more readily to the water column, where they could stimulate additional biological production. More productivity created more sinking organic matter, while greater decomposition consumed still more oxygen. A natural biological process gradually reinforced itself through this repeating cycle. This pattern did not develop everywhere with equal intensity or at the same moment. Regional differences in climate, circulation, water depth, and river discharge produced varied responses across the world's coastal seas. Forest decline and accelerating soil erosion therefore reached far beyond the continents that first experienced them. Material carried seaward reshaped marine ecosystems, steadily reducing the volume of well oxygenated water and leaving many animals confined to an increasingly limited range of habitable environments. For countless marine creatures, survival depended upon occupying a narrow range of environmental conditions. Too much heat disrupted normal body functions. Too little oxygen limited the ability to breathe. Between these extremes lay the water, where feeding, growth, reproduction, and movement remained possible. As the late Permian crisis deepened, that hospitable space steadily narrowed across many parts of the ocean. Marine scientists describe oxygen stress using two related terms. Hypoxia refers to oxygen concentrations low enough to place animals under physiological strain, even though some oxygen remains available. Anoxia describes conditions where oxygen is almost entirely absent. Few complex organisms can tolerate prolonged anoxia, while many experience declining health well before oxygen disappears completely. The transition between these states varied from one region to another, creating a patchwork of increasingly difficult habitats. At the same time, warming transformed the upper ocean. Surface waters exposed directly to prolonged heating became less favorable for many species already operating near their thermal limits. Deeper waters offered lower temperatures, yet oxygen there had declined as circulation weakened and decomposition continued consuming available supplies. Between overheated surface layers and oxygen, poor depths remained only a comparatively thin zone, where both temperature and oxygen still supported active marine life. This shrinking band is known as habitat compression because the usable environment becomes confined within progressively narrower limits. Habitat compression reshaped ecological relationships even before widespread extinction occurred. Animals sharing similar environmental requirements became concentrated into smaller volumes of water. Feeding grounds contracted as populations gathered within the remaining favorable layers. Competition for prey intensified while individuals encountered one another more frequently than before. Predators and prey occupied the same restricted spaces, increasing the likelihood of encounters that would once have been spread across a much larger portion of the water column. Reproduction also became more uncertain. Many marine species release eggs or larvae into conditions that must remain suitable for extended periods before development is complete. Adults may tolerate environmental change better than their offspring, whose delicate early stages often possess narrower physiological limits. Eggs and larvae also have little ability to escape deteriorating conditions because currents largely determine where they drift. Even when mature animals survived, successful recruitment of the next generation could decline if developing young encountered unsuitable oxygen levels or excessive warmth. Movement offered only partial protection. Many fish and swimming invertebrates could relocate over considerable distances, yet suitable conditions were not always available nearby. Large regions of the ocean experienced similar environmental pressures simultaneously, reducing the effectiveness of migration. Natural travel corridors connecting productive habitats could also become interrupted, where oxygen poor waters expanded across continental shelves or deeper passages. Different life stages frequently possessed different environmental tolerances, making successful migration even more difficult for entire populations. Life attached to the seafloor faced still greater limitations. Numerous organisms lived permanently anchored to hard surfaces or moved only short distances across the sediment. These communities depended upon local conditions remaining favorable because rapid relocation was impossible. As oxygen declined, many benthic habitats lost the stability that had supported diverse marine ecosystems for immense spans of geological time. One important record of these changing conditions appears in black shale, dark, organic, rich sediment commonly associated with oxygen poor environments. Black shale provides valuable evidence that low oxygen developed where those sediments accumulated. It does not represent a direct photograph of the entire ocean, since conditions varied substantially between different basins and continental margins. Some regions probably experienced temporary returns of better oxygenated water before unfavorable conditions developed once again. Such instability complicated recovery because ecosystems require sustained environmental stability to rebuild successfully. Even brief improvements could be followed by renewed anoxia, gradually preparing the oceans for an even more chemically hostile stage of the unfolding crisis. Not every place deprived of oxygen followed the same chemical path. In some marine basins, the disappearance of oxygen allowed an entirely different set of microscopic organisms to dominate. Their metabolism altered the surrounding water, creating conditions that excluded most familiar forms of animal life. These environments are known as euxinic waters, anoxic waters containing dissolved hydrogen sulfide. Hydrogen sulfide is a toxic chemical compound produced through certain microbial processes that occur when oxygen is unavailable. It forms naturally in many modern environments, including some stagnant sediments and restricted marine basins. During the late Permian crisis, evidence indicates that comparable conditions expanded into portions of the ancient ocean, although neither their timing nor their geographic extent remained identical from one region to another. The microorganisms responsible for producing hydrogen sulfide are known as sulfate-reducing microorganisms. Instead of using oxygen to obtain energy, they rely upon sulfate dissolved in seawater as part of their metabolism. This alternative pathway becomes advantageous only after oxygen has largely disappeared. If abundant organic matter remains available as food and water circulation fails to replenish oxygen efficiently, these microbial communities can expand and generate increasing quantities of hydrogen sulfide within affected waters. Several lines of geological evidence help scientists identify these ancient environments. Sulfur isotopes preserved within rocks record changes associated with microbial sulfur cycling. Trace metals that respond differently under oxygen-rich and oxygen-poor conditions provide another valuable indicator of changing seawater chemistry. Researchers also examine biomarkers, preserved molecules or molecular fragments associated with particular organisms or environmental conditions. Together, these independent records allow ancient marine chemistry to be reconstructed with increasing confidence. Among the most informative biomarkers are those associated with green sulfur bacteria. Certain members of this microbial group require sunlight while also depending upon hydrogen sulfide instead of oxygen. Because sunlight penetrates only the upper portion of the ocean, Evidence for these organisms suggests that sulfide rich, oxygen free water reached comparatively shallow depths in at least some marine settings. Such findings indicate that hostile chemical conditions occasionally extended much closer to the ocean surface than they do across most modern seas. Even so, available evidence does not support the idea that the entire global ocean became one continuous reservoir of hydrogen sulfide. Euxinic conditions developed unevenly through space and time. Some basins remained more severely affected than others, while local circulation, water depth, coastline geometry, and changing climate all influenced where sulfide accumulated. Neighboring regions could experience substantially different chemical environments despite belonging to the same broader ocean. Scientists have also explored whether hydrogen sulfide occasionally escaped from seawater into the atmosphere. Some models suggest that limited releases may have occurred where sulfide rich water reached the surface. The possible biological consequences of such events remain an active area of research, and the scale of any atmospheric influence has not been established with certainty. Present evidence encourages careful interpretation rather than broad conclusions about global atmospheric poisoning. The ecological consequences within the water itself are much better supported. Euxinic conditions removed habitat suitable for most complex marine animals because dissolved hydrogen sulfide is directly harmful to their tissues, while oxygen remained absent. Species already confined by warming temperatures and shrinking oxygenated zones encountered another barrier that further reduced the places where they could survive. This combination of changing chemistry and declining habitat did not affect every organism equally, helping explain why some marine groups disappeared earlier than others, while a limited number endured for longer intervals within the unfolding extinction. The fossil record preserves more than a count of vanished species. It also preserves a pattern. Some groups declined rapidly, while others endured longer before disappearing or survived the crisis altogether. This uneven outcome reveals that the extinction did not strike marine life at random. The changing environment favored certain biological traits while exposing others to mounting disadvantage. One of the most important differences among marine animals lies in metabolic demand, the amount of energy required to maintain normal life. Highly active species consume more energy than animals that spend much of their lives attached to the sea floor or moving only occasionally. Meeting that greater energy requirement depends upon obtaining a continuous supply of dissolved oxygen. Any reduction in oxygen, therefore, affects active organisms more quickly because their bodies have less margin for interruption. Rising temperatures added another challenge through thermal stress. As body temperature increases, many marine animals require additional oxygen to support faster metabolism and maintain normal physiological functions. During the late Permian crisis, these rising demands developed at precisely the same time that warming seawater naturally contained less dissolved oxygen. The relationship created a biological double bind. Oxygen supplies declined, while oxygen demand increased, steadily reducing the range of conditions under which many animals could continue functioning. Species inhabiting tropical seas may have faced particular vulnerability because many already lived close to the upper limits of temperatures they could tolerate. Even modest additional warming could push those populations beyond conditions suitable for sustained survival. Marine communities living at higher latitudes encountered a different challenge. Their environments changed rapidly as warming spread into regions that had once remained comparatively cool. Survival depended not only upon physiological tolerance, but also upon whether migration routes remained connected and whether suitable continental shelf habitats existed farther from the equator. Biological characteristics further influenced the outcome. Large animals generally required greater quantities of oxygen than smaller organisms performing similar activities. Species adapted to a narrow range of environmental conditions possessed fewer opportunities to adjust when those conditions disappeared. Many heavily calcified organisms also struggled, as changing seawater chemistry increased the difficulty of building and maintaining mineral skeletons or shells. These traits combined differently within each lineage, producing varying levels of resilience or vulnerability across marine ecosystems. Geographic distribution also mattered. Species occupying broad ranges often encountered a wider variety of environmental conditions throughout their history. Because populations already existed across different regions, some groups retained refuges where local conditions remained temporarily favorable. Organisms restricted to limited geographic areas possessed fewer alternatives if their home environment deteriorated. Ecological flexibility offered another important advantage. Generalist species capable of feeding upon many different food sources or occupying several habitat types could adjust more readily as familiar ecological relationships unraveled. Specialists depending upon one particular prey, habitat, or environmental setting frequently had fewer options once those resources became unreliable. Scientists examine these relationships using physiology based climate models that compare reconstructed environmental change with the known biological tolerances of living and extinct organisms. These models estimate where combinations of warming and declining oxygen would have exceeded the limits of different marine animals. Their predictions closely resemble many geographic patterns observed in the fossil record, suggesting that heat and oxygen loss together formed powerful drivers of extinction. Models do not replace fossils, which remain the direct record of ancient life. Their strength lies in testing whether proposed mechanisms reproduce the patterns preserved within rocks. When independent evidence points toward the same explanation, confidence grows that the underlying processes are being understood more accurately. Those processes extended beyond individual species, eventually reshaping the great biological communities whose living structures form the foundation of entire marine ecosystems. Life in the ocean depends upon more than the animals swimming through open water. Many of its richest communities grow around living structures that reshape the surrounding environment. Organisms capable of creating or modifying habitat used by many other species are known as ecosystem engineers. By building physical frameworks that endure across generations, they transform bare seafloor into places where countless forms of life can feed, reproduce, hide, and grow. During the late Permian, reef ecosystems differed markedly from the coral-dominated reefs familiar today. Their foundations were assembled by changing combinations of sponges, algae, microbial communities, and other reef-building organisms that gradually produced durable limestone frameworks. These living structures rose above the surrounding seafloor and created intricate surfaces filled with crevices, ledges, chambers, and sheltered spaces. Every new layer expanded the variety of habitats available for marine life. The ecological importance of these reefs extended far beyond the organisms constructing them. Their irregular surfaces slowed water movement in some places while accelerating it through narrow passages in others, creating a wide range of local conditions. Filter feeders benefited from flowing water that delivered suspended food. Grazing animals found broad surfaces covered with microbial growth. Juvenile organisms occupied protected cavities where currents were less intense and predators less effective. Larger hunters also depended upon these thriving communities, because concentrated prey gathered around the reef framework. Reef builders proved especially sensitive to the environmental pressures accumulating across the oceans. Elevated temperatures interfered with normal growth. Declining oxygen reduced physiological performance. Increasing sediment carried from damaged continents, buried living surfaces, and blocked access to light required by photosynthetic partners in some reef communities. Changing seawater chemistry further complicated the production of mineral skeletons and supporting structures. Each pressure acted alongside the others, making successful reef construction progressively more difficult. The disappearance of functioning reefs illustrates an important distinction between species extinction and ecological collapse. A species may continue surviving in scattered populations while no longer performing the ecological role that once sustained an entire community. Even when some reef building organisms persisted, they often lost the capacity to create extensive habitat supporting hundreds of associated species. Survival of isolated individuals could not replace the disappearance of the living architecture itself. The consequences extended through every level of the ecosystem. Grazers lost productive feeding surfaces. Filter feeders lost favorable currents generated by reef structures. Predators encountered fewer concentrated hunting grounds as prey communities dispersed or vanished. Juvenile animals lost sheltered nursery habitats that had protected vulnerable early life stages. The disappearance of one ecological foundation therefore triggered many additional losses among species that had never constructed reefs themselves. Similar changes unfolded across other seafloor environments. Extensive brachiopod beds diminished. Crinoid communities declined in many regions. Burrowing ecosystems that had continually reworked marine sediment also became greatly simplified. This reduction affected bioturbation, the natural mixing of sediment by animals moving, feeding, and excavating beneath the seafloor. Healthy marine sediments normally contain countless burrows carrying oxygen and organic matter downward while bringing buried material upward. As burrowing animals declined, sediments remained less disturbed and deeper layers became increasingly isolated. Post-extinction seafloors preserved evidence of this simplification through the scarcity of deep burrows and the reduced diversity of trace fossils left behind by sediment-dwelling organisms. Complexity itself became one of the casualties of the crisis. Habitats that had once supported intricate biological interactions gave way to more uniform environments with fewer ecological roles and diminished structural variety. As these living frameworks disappeared, attention turns naturally toward another process that may have further challenged organisms already struggling to build shells and skeletons within an increasingly altered ocean. The chemistry of seawater changes whenever the atmosphere changes above it. Oceans continually exchange gases with the air, absorbing part of the carbon dioxide released into the atmosphere. Once dissolved, carbon dioxide reacts with seawater to form a series of chemical compounds that lower the water's acidity scale value, known as pH, while also reducing the availability of carbonate ions. These reactions unfold naturally today and almost certainly occurred during the environmental upheaval of the late Permian. Ocean acidification can sound more dramatic than the chemistry itself. The term does not mean seawater transforms into a corrosive liquid resembling industrial acid. Even after substantial chemical change, seawater remains alkaline. The important shift lies in the gradual reduction of carbonate ions, one of the essential building materials used by many marine organisms. As carbonate becomes less available, producing mineral shells and supporting skeletons can require more energy, especially for species already living near their physiological limits. Carbonate ions play a central role in the biology of numerous marine organisms. Many heavily calcified animals rely upon them to construct protective shells or rigid frameworks that support their bodies. Some species possess greater ability to regulate their internal chemistry, allowing partial compensation when surrounding seawater changes. Others appear much less capable of maintaining those conditions, making them potentially more vulnerable if carbonate supplies decline over extended periods. Scientists investigate these ancient chemical changes through several independent lines of evidence. One important approach examines boron isotopes preserved within marine carbonates because their proportions can reflect the acidity conditions present when minerals formed. Other proposed indicators attempt to reconstruct seawater chemistry from fossil shells, sediment composition, or additional geochemical signatures. Together, these records provide valuable clues, although none offers a perfectly complete picture of global ocean conditions. Each proxy carries important limitations. Geological preservation may alter original chemical signals after burial. Local environmental conditions can influence measurements independently of broader global trends. Calibration methods also introduce uncertainty because researchers must relate modern observations to oceans that differed substantially from those of the late Permian. These factors require careful interpretation before broad conclusions are drawn about the magnitude or geographic extent of ancient acidification. As a result, scientific discussion remains active. Some studies report evidence consistent with severe acidification across substantial portions of the ocean, accompanied by biological responses expected from declining carbonate availability. Other investigations find that several anticipated biological indicators are absent, weak, or inconsistent with a uniformly intense global acidification event. A comprehensive analysis, published during the early years of the present decade, concluded that several expected biological signatures of severe worldwide acidification were missing from the record it examined, illustrating that important questions remain regarding the scale and lethality of this process. Even if acidification varied across different regions, its influence may still have been significant when combined with other environmental pressures already affecting marine ecosystems. Organisms challenged by warming temperatures and declining oxygen could have possessed less physiological capacity to cope with additional chemical stress. Multiple moderate burdens, acting together, may have produced greater biological consequences than any one factor operating in isolation. Current evidence supports different levels of confidence for different parts of the extinction story. Massive volcanism in Siberia remains strongly supported as the initiating trigger. Major global warming is also strongly supported, as is widespread marine oxygen loss. The precise severity, distribution, and biological importance of ocean acidification remain less firmly resolved. Recognizing that distinction strengthens scientific understanding because reliable knowledge depends upon separating robust conclusions from questions that continue inviting careful investigation. From that foundation, the rocks themselves preserve the direct record of which organisms ultimately endured and which disappeared. One hillside in southeastern China preserves one of the clearest chapters in Earth's geological archive. Layer upon layer of marine sediment accumulated there across the closing moments of the Permian period and the opening of the Triassic. Within those rocks, countless chemical traces and fossil remains document a transformation so profound that scientists from around the world agreed to recognize this location as the official reference for one of the greatest turning points in planetary history. This site, known as Meishan, contains the internationally accepted global boundary stratotype section and point for the Permian Triassic boundary. A global boundary, stratotype, section, and point is an agreed reference location used by geologists to define the precise boundary between two intervals of geological time. Rather than relying upon different local rock sequences scattered across continents, researchers compare observations with this carefully studied standard, ensuring that discoveries made elsewhere can be placed within the same global framework. The succession of rocks at Meishan records changing marine conditions with exceptional detail. Thin sedimentary layers preserve abundant fossils representing the organisms that once inhabited nearby seas. Volcanic ash beds appear at several levels within the sequence, providing valuable material for determining age. Chemical signatures preserved throughout the sediments reveal changing environmental conditions while biological communities rose, declined, and disappeared across a comparatively brief interval in geological history. Among the most important tools used to establish the timing of these events is high precision uranium lead dating performed on zircon crystals preserved within volcanic ash. Zircon is especially valuable because it incorporates uranium atoms into its crystal structure when it forms while excluding lead. As radioactive uranium gradually decays into lead at a predictable rate, the changing proportions function as an exceptionally reliable geological clock. Measurements from these crystals place the Permian Triassic boundary at approximately 251.9 million years ago. The fossil record indicates that the principal marine extinction interval unfolded rapidly in geological terms. Although the crisis still occupied thousands of years, that duration represents only a brief moment within Earth's immense history. Marine ecosystems changed far more quickly than the surrounding rock layers might initially suggest. Estimating the scale of biological loss requires careful attention to terminology. Many studies conclude that more than two-thirds of marine animal genera disappeared during the extinction. Species level estimates commonly approach between 80 and 90%. These figures differ because a genus includes one or more closely related species. A genus can survive even after losing several constituent species, making genus and species statistics describe different aspects of biodiversity. Interpreting fossils also involves recognizing the Singer-Lipps effect, a pattern in which incomplete fossil sampling makes an abrupt extinction appear more gradual than it actually was. Organisms are rarely preserved immediately before their final disappearance, leaving natural gaps within the geological record that can blur the precise timing of extinction. Among the greatest losses were the last surviving trilobites, whose diversity had already declined substantially during earlier intervals before the end-Permian crisis eliminated their remaining lineages. Many brachiopods vanished. Rugose and tabulate corals disappeared entirely. Numerous crinoid groups declined sharply. Many ammonoid lineages ended, along with fusulinid foraminifera that had flourished for millions of years. Statistics alone cannot fully describe what these rocks record. The disappearance of entire combinations of interacting organisms transformed ecosystems in ways that simple percentages cannot capture. Marine communities preserved at Meishan reveal not only which creatures vanished, but also how the fabric of ancient life itself was fundamentally rearranged before the equally intricate story preserved across the continents comes into view. Across the plains of what is now South Africa, layers of rock preserve a slower rhythm than the dramatic losses recorded in many marine sediments. The record does not point to every terrestrial community disappearing within a single instant. Instead, it reveals a drawn out sequence of ecological change, with familiar animals becoming less common, communities shifting, and landscapes gradually assuming a different character over an extended span of time. Much of this understanding comes from the Karoo Basin, one of the world's most important archives of late Permian and early Triassic land life. Paleontologists divide its fossil bearing rocks into fossil assemblage zones, intervals identified by characteristic groups of animals that commonly occur together. These zones allow scientists to compare changing ecosystems through successive layers and recognize how communities evolved as environmental conditions changed. Among the final Permian intervals is the Daptocephalus assemblage zone. Its rocks preserve established ecosystems inhabited by large dicynodont herbivores browsing across floodplains, formidable Gorgonopsian predators occupying the highest positions within food webs, diverse therocephalians filling several ecological roles, and amphibians living along rivers and wetlands. Together, they represent communities that had developed through long periods of evolutionary stability before environmental pressures intensified. The transition away from these communities appears more gradual than a single dividing line might suggest. Different species vanish from different layers, while changing abundances reveal populations declining before complete disappearance. Evidence from portions of the South African record indicates that many losses unfolded across approximately 1 million years rather than during one sharply defined moment. Such timing reflects the regional geological record and should not automatically be applied to every continent or every ecosystem. Regional differences arise for several reasons. Sedimentation rates vary from one basin to another, causing some intervals to accumulate thick deposits, while others preserve relatively little. Gaps in deposition may remove parts of the history altogether. Local climate conditions differ across landscapes, influencing which organisms survive longest. Fossil preservation also depends upon whether bodies become buried under suitable conditions. These factors mean separate terrestrial records rarely capture identical sequences of events. As communities changed, shifts appeared in both abundance and body size. Large vertebrates became less common in many assemblages, while surviving populations often occupied simplified ecological networks. Plant communities also changed as environmental stress altered dominant vegetation, influencing the stability of river systems that depended upon established root networks. River channels, floodplains, and surrounding habitats responded together, linking biological turnover with broader landscape transformation. Calculating a precise global percentage for terrestrial extinction remains far more difficult than for marine life. Land fossils are preserved less continuously because erosion, changing rivers, and interrupted sediment accumulation frequently remove important intervals. Scientists therefore possess a patchier record than the comparatively continuous successions preserved beneath many ancient seas. Family level estimates, commonly used for land vertebrates, also cannot be compared directly with marine species level estimates because they measure biodiversity at different taxonomic scales. Even without assigning a single worldwide percentage, the overall conclusion remains well supported. Dominant terrestrial vertebrate communities underwent profound reorganization. Gorgonopsians disappeared completely. Many dicynodont and therocephalian lineages suffered severe reduction or vanished altogether, although a limited number persisted beyond the crisis. Landscapes that once supported diverse, large-bodied animals gave way to ecosystems with fewer dominant herbivores, fewer apex predators, and simpler food webs. Within those altered environments, survival increasingly depended upon biological characteristics that enabled a minority of organisms to endure conditions that many of their former neighbors could no longer withstand. The aftermath of a mass extinction rarely rewards the largest, fastest, or most imposing creatures. The familiar phrase, survival of the strongest, does not describe what unfolded across the closing stages of the Permian. Natural selection favors traits suited to immediate environmental conditions, whatever those conditions happen to be. During this crisis, flexibility often mattered more than dominance, and endurance became a quality measured by adaptation rather than power. Many characteristics may have improved the chances of persistence, although none provided certainty. Small or moderate body size reduced the total amount of food an animal required to remain alive. Broad diets allowed organisms to shift between available food sources as familiar plants and prey disappeared. Wide geographic distributions increased the likelihood that at least some populations occupied regions where conditions remained temporarily favorable. Burrowing behavior offered protection from extremes at the surface, while rapid maturation and high reproductive output helped replace losses more quickly. Physiological tolerance of elevated temperatures or reduced oxygen also became increasingly valuable as environmental conditions continued to fluctuate. Smaller animals possessed particular advantages in landscapes where food supplies became unreliable. Their lower overall energy requirements allowed them to survive on resources that could no longer support much larger bodies. Even modest reductions in daily nutritional needs could influence whether a population endured through prolonged ecological disruption. Smaller size, however, also carried disadvantages. Small bodies generally lose water more rapidly than larger ones, creating additional challenges wherever drying climates or unstable freshwater supplies developed. Every apparent advantage, therefore, came with its own biological costs. The fossil record reflects this complexity. No single characteristic guaranteed survival across every habitat or every continent. Species sharing similar body size sometimes experienced very different outcomes. Burrowing organisms frequently persisted, although many disappeared as well. Broad distributions often improved resilience, yet some geographically widespread groups still declined. Survival emerged from combinations of traits interacting with local environmental circumstances rather than from one universal formula. Paleontologists use the term disaster taxa to describe organisms that become unusually abundant after ecological collapse. These species thrive within disturbed environments where many former competitors have vanished. Their success should not be mistaken for evidence that they dominated ecosystems before the extinction. Frequently, they occupied comparatively modest roles beforehand, expanding only after ecological opportunities suddenly became available. Marine environments preserve several examples of disaster taxa. Certain bivalves spread widely across newly simplified seafloors. Opportunistic ammonoid lineages diversified rapidly within ecosystems that had lost much of their previous complexity. Microbial communities also expanded across some marine sediments, creating broad microbial mats that covered areas once heavily occupied by burrowing animals and grazing invertebrates. These microbial mats flourished because several ecological processes weakened simultaneously. Grazing animals that normally consumed microbial growth became far less abundant. Burrowing organisms no longer mixed sediment as effectively, allowing stable microbial layers to remain undisturbed for longer intervals. Continued environmental stress further limited the return of more complex communities capable of disrupting these expanding surfaces. In many places, seafloor conditions began to resemble ecosystems far older in Earth's history. Before intensive burrowing and grazing had transformed marine sediments into the dynamic habitats familiar throughout much of the later Paleozoic. Even so, persistence should never be confused with ecological recovery. A species can survive while remaining one of only a handful of organisms occupying an impoverished environment. Recovery requires many interacting species rebuilding food webs, restoring habitat, and reestablishing the ecological relationships that allow diverse communities to function. That process unfolds much more slowly than simple survival. Among the terrestrial animals that cross this difficult threshold, one unassuming herbivore would come to define the earliest world after the extinction, the remarkable dicynodont known as Lystrosaurus. Among the animals that crossed the boundary between the Permian and the Triassic, one stocky herbivore came to symbolize survival in a transformed world. Lystrosaurus was a dicynodont therapsid with a broad beak, suited for cropping vegetation, and, in many individuals, a pair of forward projecting tusks. Its sturdy limbs supported a compact body carried close to the ground, creating an appearance that seemed unremarkable beside the extraordinary predators and giant herbivores that had dominated earlier ecosystems. Its remains have been discovered across much of southern Pangaea, including Africa, India, Antarctica, and several neighboring regions. Long before modern plate tectonics became widely accepted, these remarkably similar fossils puzzled researchers because they appeared on continents now separated by immense oceans. Their distribution later became important evidence, supporting continental drift, demonstrating that these distant landmasses had once formed parts of a connected supercontinent where animals could move across continuous landscapes. Within several well-studied early Triassic fossil assemblages, Lystrosaurus appears with striking frequency. This abundance has sometimes been simplified into claims that it represented nearly all land vertebrates everywhere after the extinction. The fossil record does not support such a universal statement. Instead, it shows that Lystrosaurus became extraordinarily abundant in several carefully sampled regions, while other areas preserved different community compositions. Its prominence remains remarkable without requiring exaggerated percentages. Scientists have proposed several characteristics that may have contributed to this success. A broad diet would have allowed feeding upon a variety of available plants when preferred foods became scarce. Its strong beak could process tough vegetation growing under difficult environmental conditions. A wide geographic distribution increased opportunities for some populations to survive regional environmental change. Certain anatomical features have also encouraged the suggestion that Lystrosaurus possessed useful tolerance for stressful climatic conditions, although the exact physiological mechanisms remain uncertain. Burrowing behavior has received particular attention. Fossil burrow associations and aspects of the skeleton provide evidence consistent with digging ability. Strong forelimbs and robust shoulder construction support this interpretation, suggesting that at least some individuals excavated underground shelters. Such refuges could have moderated exposure to temperature extremes or seasonal environmental stress. Even so, many details of everyday behavior cannot be observed directly. Burrows preserve valuable clues, although they do not reveal every aspect of how these animals lived across changing landscapes. Growth studies provide another perspective. Microscopic examination of bone tissue suggests that Lystrosaurus often grew rapidly, particularly during early life. Rapid development allows individuals to reach reproductive age sooner, helping populations recover more quickly after repeated losses. Earlier reproduction can be especially valuable when mortality remains high because each generation gains additional opportunities to produce offspring before environmental conditions deteriorate again. The world supporting these expanding populations differed greatly from the ecosystems that had preceded it. Vegetation remained sparse across many regions, recovering from ecological disruption. River systems shifted unpredictably through landscapes still responding to climatic instability. Large predators had become less diverse, while repeated environmental stress continued limiting ecological complexity. Food webs contained fewer interacting species, leaving many ecological roles temporarily vacant. Ecologists describe this situation as ecological release. When competitors and predators disappear, surviving organisms gain access to resources that were previously contested. Lystrosaurus did not rise because it conquered a thriving world filled with flourishing rivals. Its expansion unfolded across environments where much of the former ecological structure had already vanished. Even this remarkable success belonged to a planet still enduring the consequences of the crisis, where survival marked only the beginning of a much longer journey through the challenging years of the early Triassic. The boundary between the Permian and the Triassic marks the beginning of a new geological period, yet the rocks reveal little sign that life entered a calmer chapter. Crossing that boundary did not restore stable climates or flourishing ecosystems. The extinction itself reached its greatest intensity near this transition, although the environmental forces that had reshaped the planet continued influencing oceans, continents, and atmosphere for millions of years afterward. The earliest Triassic unfolded beneath an exceptionally warm global climate, often described as a super greenhouse. Average temperatures remained elevated across much of the planet, while tropical regions experienced especially severe heat that challenged organisms already living near their physiological limits. Conditions favorable for rebuilding complex ecosystems remained uncommon because many habitats continued experiencing environmental stress long after the principal extinction interval had passed. Chemical records preserved within rocks also reveal repeated carbon cycle oscillations during this time. These oscillations reflect irregular movement of carbon among the atmosphere, oceans, rocks, and living organisms rather than a stable balance. Instead of settling into a lasting equilibrium, Earth's interconnected systems shifted repeatedly, suggesting that feedback processes continued disturbing global environmental conditions across successive intervals. Marine environments preserve additional evidence of continuing instability. Oxygen depleted waters expanded repeatedly through parts of the oceans, producing recurring episodes of marine anoxia rather than one isolated event. Sedimentary records from several regions indicate that environmental crises returned more than once after the extinction boundary. These repeated disturbances interrupted biological recovery before diverse communities could become firmly established, forcing surviving organisms to persist through changing conditions that remained difficult and unpredictable. The prolonged absence of familiar ecosystems appears in two striking geological patterns. One is the reef gap, an extended interval during which complex reef systems remained uncommon despite the survival of some reef-building organisms. Another is the coal gap, a period when widespread coal formation became greatly reduced because extensive peat-forming wetlands had not yet recovered across many landscapes. Together, these patterns reveal that ecological rebuilding lagged far behind simple survival of individual species. Communities that did develop often displayed low diversity, with relatively few resilient organisms occupying habitats once shared by many interacting species. Ecological dominance shifted repeatedly. One species could become abundant for a time, only to decline after another environmental change altered local conditions. Success, therefore, remained temporary, reflecting continued instability rather than long lasting ecological balance. Many surviving groups also exhibit what paleontologists call the Lilliput effect, a temporary tendency towards smaller, average body sizes following a mass extinction. Several explanations have been proposed. Limited food resources may have favored organisms requiring less energy. Elevated temperatures and recurring oxygen shortages could have constrained growth. Selective survival of naturally smaller species may also have contributed. In some lineages, evolutionary pressure toward earlier reproduction may have favored reaching maturity before environmental conditions deteriorated again. Evidence indicates that no single explanation applies everywhere, and the Lilliput effect varied considerably among different organisms and different regions. These continuing changes demonstrate that crossing the extinction boundary represented only the first stage of survival. Escaping the initial crisis offered no guarantee of long term persistence because repeated environmental disruptions continued testing populations across the earliest Triassic. Many lineages that endured the boundary itself disappeared during these later intervals, while others survived only through remarkable flexibility across changing habitats. Recovery therefore unfolded as a prolonged process rather than a single turning point. Before richly connected ecosystems could return, food webs needed to regain complexity, habitats had to become more dependable, and countless ecological relationships required time to form again within a world that remained unsettled for millions of years. A handful of surviving species may suggest that life had endured, yet endurance alone could never restore a living world. The return of biodiversity required far more than crossing the extinction boundary. It depended upon countless relationships being rebuilt, one generation after another, until communities once again formed interconnected systems capable of supporting rich ecological complexity. The first stage was survival. A lineage survived if it persisted through the crisis without disappearing entirely. Even a very small population could preserve the possibility of future expansion, provided environmental conditions allowed continued reproduction. Survival, therefore, represented continuity, not recovery. Many lineages achieved this first step while remaining scarce and vulnerable for long periods afterward. The second stage was taxonomic recovery. During this phase, surviving lineages diversified, producing increasing numbers of species as populations expanded into newly available ecological opportunities. The growing total of species reflects renewed evolutionary activity, although those species may still occupy comparatively simple ecosystems. Rising diversity alone does not reveal whether food webs, habitats, or ecological interactions have regained their former complexity. The third stage was ecological recovery. This required the return of intricate biological relationships that connected organisms across entire landscapes and oceans. Reef builders needed to establish stable structures before many marine inhabitants could return. Large predators depended upon dependable prey populations that had themselves become abundant enough to sustain higher levels of the food web. Deep burrowing animals restored sediment mixing that benefited numerous smaller organisms. Forest-forming plants gradually recreated extensive habitats supporting herbivores, decomposers, and the many species associated with mature vegetation. None of these transformations could happen immediately. Evolution works with variation already present within populations. Mutations also introduce new variation across successive generations. Natural selection gradually alters populations as individuals possessing favorable characteristics leave more descendants than others. Increasing ecological specialization demands repeated evolutionary refinement, shaping organisms to occupy particular roles within increasingly complex communities. Such changes unfold across immense spans of time rather than within a few generations. These processes also depend upon chains of biological relationships. A predator cannot establish a lasting population without sufficient prey. Reef-dwelling animals require reef builders to create the physical framework, supporting diverse marine life. Large herbivores flourish only where productive vegetation grows consistently enough to sustain them. Each recovery depends upon another, producing a network of mutual dependence that cannot be reconstructed in isolation. Environmental instability repeatedly interrupted this rebuilding. Continuing episodes of extreme warmth and recurring marine oxygen depletion disrupted recovering populations before ecological networks could fully mature. Communities beginning to diversify often encountered renewed environmental stress, forcing another cycle of decline and adaptation instead of uninterrupted expansion. Some groups nevertheless responded with remarkable speed. Early Triassic ammonoids diversified relatively quickly, producing many new forms after the extinction. Their rapid taxonomic recovery demonstrates that evolutionary diversification can proceed even while broader ecosystems remain simplified. Expanding numbers of ammonoid species did not mean that marine communities as a whole had regained their previous structure or resilience. Marine reptiles appeared and diversified later during the Triassic, adding entirely new components to recovering oceans. Even so, the widespread return of complex reefs, large-bodied predators, and intensively burrowed seafloors required much longer intervals before becoming established once again. Marine biodiversity remained substantially reduced for roughly 5 million years. That interval exceeds the entire existence of the human genus, illustrating the immense duration required for ecological systems to regain complexity after profound disruption. Ecosystems possess histories built through innumerable interactions accumulated across evolutionary time. A few surviving species preserve the possibility of renewal, although they cannot recreate those histories within the span of a single age. From that prolonged rebuilding emerged a world unlike the one that had vanished, carrying both familiar descendants and entirely new ecological possibilities. Geologists divide Earth's history into great eras because the rocks themselves reveal moments when life changed so profoundly that the planet entered a different biological chapter. The close of the Permian marks one of those rare turning points. Beyond that boundary begins the Mesozoic era, a world connected to what came before by ancestry, yet transformed so completely that many familiar communities would never return. The names of these eras reflect that transition. Paleozoic means ancient life, referring to the long age during which many foundational marine and terrestrial ecosystems developed. Mesozoic means middle life, identifying the era that followed after those earlier communities had been fundamentally reshaped. These divisions are not chosen arbitrarily. They arise from changes preserved within rock layers and fossil assemblages, where disappearing lineages and newly expanding groups provide a permanent record of biological transformation through deep time. Many defining organisms of the Paleozoic vanished forever. Trilobites, whose ancestors had inhabited the oceans for hundreds of millions of years, disappeared completely. Rugose and tabulate corals never returned to construct reefs again. Numerous brachiopod communities that had dominated marine seafloors for immense spans of time became greatly diminished. On land, Gorgonopsians also vanished, ending an evolutionary branch that had once occupied the highest predatory roles across extensive regions. Other groups gradually expanded into opportunities left behind. Bivalves became increasingly important across many marine environments. Newly evolving ammonoid lineages diversified within recovering seas. Archosauromorph reptiles began exploring ecological roles that earlier competitors had occupied. Surviving therapsids also continued evolving, preserving part of a lineage that would eventually include mammals many millions of years later. None of these groups entered an unchanged world. Each expanded within ecosystems whose previous structures had already been profoundly altered. This transition should not be understood as replacement through progress. Evolution does not move toward predetermined goals or supposedly superior forms. Organisms succeed because their inherited characteristics match existing environmental conditions better than those of competing species. When climates, habitats, and ecological relationships change, different biological traits become advantageous. Evolution, therefore, reflects continual adaptation to changing circumstances rather than movement toward increasing perfection. An important ecological principle helps explain why these transformations occurred. Established groups often prevent newcomers from occupying the same ecological roles, a phenomenon known as ecological incumbency. Species already thriving within particular habitats consume available resources, reproduce successfully, and maintain stable populations that leave little opportunity for potential competitors. Mass extinction removes many of these incumbents. Ecological roles that remained occupied for millions of years suddenly become available, allowing surviving lineages to diversify into environments that had previously been inaccessible. The resulting planet remained unmistakably Earth. Rivers still crossed continents. Oceans continued circulating around the globe. Forests slowly returned across suitable landscapes. Even so, the living communities inhabiting those environments followed new evolutionary pathways. Familiar ecological patterns reappeared only after being assembled from different combinations of organisms, creating ecosystems that resembled earlier ones in function while differing substantially in biological composition. Every extinction also erased unique evolutionary history. When an entire lineage disappears, its distinctive anatomy, developmental pathways, inherited behaviors, and evolutionary potential disappear with it. Descendant species can never recreate those exact combinations because the branching history that produced them has ended permanently. Evolution continues, although it proceeds from the surviving branches rather than from those already lost. As biodiversity gradually increased during the Triassic, the living world regained richness without recovering its former identity. Diversity returned through newly assembled communities instead of reconstructed Paleozoic ecosystems. From that reorganized foundation, additional evolutionary experiments would unfold, eventually including reptilian lineages that would become increasingly prominent within the changing landscapes of the Mesozoic era. The landscapes of the Triassic did not awaken beneath the footsteps of dinosaurs. Their story began much later, after millions of years filled with competition, experimentation, and changing climates. The end of the Permian opened evolutionary possibilities, yet those possibilities remained unwritten. Many different groups still shared the recovering world, each carrying its own history into an uncertain future. Among the reptiles present during this interval were the archosaurs, a broader evolutionary group that would eventually include crocodilians, dinosaurs, and birds. Their early relatives formed only part of a much larger biological community. They did not become immediate rulers after the extinction. Across many terrestrial ecosystems, Lystrosaurus remained abundant, while cynodonts, therocephalians, temnospondyl amphibians, and numerous reptile lineages continued occupying important ecological roles. The recovering continents supported a mixture of survivors rather than a single dominant dynasty. Competition shaped every stage of this rebuilding. Herbivores searched for recovering vegetation, predators pursued available prey, and expanding populations encountered rivals wherever ecological opportunities overlapped. Some evolutionary branches flourished briefly before declining again. Others remained uncommon for long intervals before later diversifying. Ecological roles shifted repeatedly as environmental conditions continued changing across the Triassic world. Within this setting, archosauriform reptiles gradually diversified through an evolutionary expansion known as the archosauriform radiation. New body forms appeared, along with increasing variation in posture, feeding strategies, and movement. This diversification unfolded across millions of years instead of during a sudden biological revolution. Each successful lineage emerged through ordinary evolutionary processes acting across many generations rather than through a single transformative event. The earliest dinosaurs appeared approximately 20 million years after the end-Permian extinction. Depending upon the fossils examined and the definitions applied, many paleontologists place their earliest well-supported appearance around 233 million years ago during the late Triassic. By that time, Earth had already experienced an immense interval of ecological rebuilding, evolutionary diversification, and continuing environmental change. Even then, dinosaurs did not immediately dominate terrestrial ecosystems. Their broader success came later, after another mass extinction near the close of the Triassic eliminated many competing groups. That subsequent crisis created additional ecological opportunities, allowing dinosaurs to expand across habitats where numerous rivals had disappeared. Their eventual prominence, therefore, depended upon more than one turning point in Earth's history. The sequence of events becomes clearer when viewed across deep time. Volcanoes did not erupt, Permian animals vanish, and dinosaurs immediately inherit the planet. Instead, Permian ecosystems collapsed. Surviving groups diversified into newly available ecological roles. Fresh competitors emerged from those surviving branches. Additional environmental changes and later extinction events continued reshaping evolutionary possibilities before dinosaurs became widespread. This long sequence also reveals the importance of contingency in evolution. History depends upon which lineages survive, which environments persist, and which opportunities appear at particular moments. Had a different collection of organisms crossed the Permian boundary, the biological character of the Mesozoic might have unfolded along very different paths. Evolution follows available possibilities instead of predetermined destinations. One surviving branch carried another remarkable legacy. Although the extinction removed most large synapsid rulers, smaller cynodont relatives continued evolving through the Triassic. From this enduring lineage, mammals eventually emerged. Every mammal alive today traces its ancestry through those resilient synapsids that persisted despite overwhelming loss. The catastrophe therefore erased many dominant branches while preserving another that would ultimately include every human, whale, bat, elephant, and mouse, a reminder that the deepest consequences of mass extinction often reveal themselves only after immense stretches of evolutionary time. The journey began in landscapes filled with flourishing forests, intricate reefs, and animal communities shaped through immense spans of evolutionary time. Those places belong to the late Permian, and although Earth continued turning through space after their disappearance, those particular living worlds never returned. Their foundations had been assembled across millions of years, then dismantled within a comparatively brief geological interval. What followed carried echoes of the past, yet never recreated its original form. Earth itself survived the catastrophe. Continents remained, oceans endured, mountains continued, rising and eroding beneath familiar physical laws. Life also survived. Plants, animals, fungi, and microorganisms crossed the boundary through scattered lineages that persisted despite extraordinary environmental upheaval. These statements are entirely true, although by themselves they can conceal the magnitude of what vanished during the crisis. Planetary survival differs profoundly from ecological continuity. A biosphere may remain alive while losing most of its established communities. Entire evolutionary lineages can disappear forever, taking with them distinctive anatomy, inherited developmental pathways, and ecological roles that no later organism can reproduce exactly. Habitat structures built across millions of years can also vanish, leaving descendants to begin again from greatly simplified foundations. Survival, therefore, preserves possibility without preserving everything that once existed. Deep time places this contrast into perspective. The principal extinction interval occupied only a brief moment when measured against the age of Earth. Recovery unfolded across millions of years afterward, requiring evolutionary diversification, ecological rebuilding, and gradually increasing environmental stability before richly interconnected ecosystems could emerge once more. Geological time compresses catastrophe into a narrow layer of rock while expanding recovery across countless succeeding generations. Resilience is often misunderstood because the word suggests complete restoration. Biological resilience means that certain evolutionary processes continue despite overwhelming disruption. Reproduction persists. Populations adapt. Natural selection shapes surviving lineages. New ecosystems eventually form. None of these processes erase permanent losses. Resilience allows life to continue, although it cannot recover every vanished branch of evolutionary history or reconstruct every ecological relationship exactly as it once existed. Looking back across the chain of events reveals how thoroughly Earth's systems remained connected. Rock melted beneath Siberia, carbon moved into the atmosphere, climate and ocean circulation changed. Forests weakened across broad regions, soil washed into rivers, marine waters lost oxygen across expanding areas. Ecological networks gradually came apart as one environmental change amplified another. No forest, shoreline, floodplain, or seafloor existed independently from the larger Earth system surrounding it. Disturbance in one part of that system spread through many others until biological communities across the planet experienced its consequences. Even within this unraveling, survivors carried evolutionary history across the boundary. Every living mammal, bird, reptile, amphibian, fish, and plant descends from lineages whose ancestors endured those ancient environmental bottlenecks. Their genomes and evolutionary histories reflect countless generations that persisted through changing conditions before giving rise to the diversity inhabiting Earth today. Modern species are not direct witnesses to the Permian world, Yet they exist because earlier branches successfully continued where so many others ended. The end of the Permian stands among the greatest turning points in the history of life, not because Earth became lifeless, but because life continued upon a planet where nearly every familiar biological structure had been taken apart. Recovery brought new forests, new oceans, and new ecological relationships, although it never restored the vanished world that came before. What emerged afterward was not the return of the old world. It was the beginning of another one.